Okay, let's see, camera's out of focus. Maybe if I move this, you'll not only get the whole picture, but it'll stimulate the camera to go into focus, and that seems to work. Okay. So again, we got this quiz. Initial velocity at 53 degrees, magnitude 20 meters per second. We immediately determined that the x and y components of the initial velocity would be 12 meters per second and 16 meters per second. Then we can write out the R of t. Just integrate 12 meters per second with respect to t. What do you get? You get 12 meters per second times t plus your initial position, plus an integration constant. The integration constant is your initial position. If you assume implicitly that your initial position is here, then you don't have to write any constant there. Okay. If you then integrate 16 meters per second times j, you have to integrate it twice. No, you just have to integrate once. You get, anyhow, you get this. Okay, there's your position. Here's your acceleration, which you know, and right there's the antiderivative of your 16 meters per second. We implicitly assume that at this point, since we didn't write any initial position down, since we didn't write the constant here, we immediately assume then that this is the initial position. If we want to assume that the initial position is with respect to the y position of the final impact, then we'd have to write an 80 meters plus this, and there'd be your y coordinate. Okay. So in general, if you know V naught and theta, you're going to be able to get V naught x and V naught y. You're going to get this, and you're going to be able to write down your position function in terms of initial velocity and acceleration. Now, I wrote down no constant here, which tells me that that means this equation corresponds to initial position here. Then here I wrote down 80 meters plus this, which means that my initial position would be down here. Okay. Your choice. Equally valid either way. You're going to get the same solution. You want to figure out when the thing hits here. You don't have to figure out how high it goes to figure out what the velocity is going to be here. That's how you're using the V naught, VF squared equals V naught squared plus 2A delta X or whatever, delta S. Okay. Yeah, that's essentially what you're doing if you write it out this way. Okay. And it works out that way. But, you know, for this equation, you want to solve for when this position is 0. Okay, because again, when I put the 80 meters into here, I'm assuming an initial position down here. So when your initial when your y position is 0, that's going to put you down here, and that's going to be the time when your final velocity. Well, that's going to be the time when you calculate the final velocity. Okay. So this is going to give you an equation. Simple equation, set this equal to 0. That's when the velocities, that's when the thing hits. That's when you're going to get your final velocity. You never have to do anything with the x component until you find the final velocity, because you can get the y component of your final velocity. You can do that using V naught squared equals VF squared is V naught squared plus 2A delta S. okay? But you can do that in a more sophisticated and general way if you do this. And I'm really advocating this because most of you have multivariable calculus in your future and you don't understand what you need to understand about vector functions, okay? And if you understand this multivariable calculus, you're going to be miles ahead, okay? Now, that's not the only reason. I'm doing it for good physics reasons too, because it's the simplest setup. You don't have to mess with this equation of motion and that equation of motion and everything. If you understand how these conditions lead to these equations, you know that your position vector is going to have y component 0 if you're using this R2 model, or that it's going to have y component negative 80 meters if you're using this R1 model. Does that make sense? Yeah, it's the y position. Okay. Okay, so you solve that, you get a t. You know, this equation is going to be equal to 0, or this is going to be equal to negative 80 centimeters, right? Or 80 meters, okay? So if you use this one, the position is going to be negative 80 meters because your initial position is here. Your y position is going to go down 80 meters. And at no point do you have to figure out the top. Although you can very easily once you get the equation. And if you want to figure out how high it goes, you take the derivative of this, you get your velocity function and set it equal to 0. It gives you time when you're at the peak. Plug that into your position, you get the position when it reaches the peak. Okay. So anyhow, you can use this model, you can use this model, and solve it all in one fell swoop without doing anything extraneous. Okay. Try to get your head around that. It will be very beneficial to you in this course. Just gives you a simple. It looks complicated if you're not used to it, but it's really simple once you get used to using it and understand it. Okay. And again, it's going to be of great benefit to you in multivariable calculus. Okay. Now, the other thing you got to do if you want to get VF, so yeah. That's a bad looking out there. You're just going to plug the time you get when you solve this equation into your velocity function. And you're going to get an x and a y component. Then you're going to use Pythagorean identity. And your final theta is just the arctangent of your y over x components of your velocity. You know, I mean, here's your final velocity. Byf is going to be negative. So you take the arctangent of a negative. The arctangent of a negative gives you an angle between negative 90 degrees and 0. Or negative 3 pi, negative pi over 2 and 0, whatever. Okay. There it is. Right there's the whole picture. There's your final velocity. That's just before impact. After impact, the acceleration changes and these equations no longer hold. Okay. So at the very instant of impact, these equations cease to apply. You've exceeded the domain of your model. The domain is the t-values that apply to this model. This is a uniform acceleration model. As soon as the acceleration becomes non-uniform, your domain ceases. Okay, you're out of your domain. Make sense? Just a whole model of functions and everything, vector functions. It all comes together in an example like this. Okay, now what I really want to know is what we're really getting at. And I mainly want you to think about this. What's the net force at a point on this arc? Okay, so if we assume a mass m, net force at a point on the arc is, the answer I got was two forces, air friction and gravity. Okay, and that's right. But if we're using these equations, we're ignoring air friction. Okay, so for this model, which works pretty well, if this is a 30-pound cannonball, air friction is very nearly negative. It probably doesn't make a difference of a centimeter in the position at any point of this arc. Now, I haven't worked out the differential equations. Y'all are learning differential equations as we speak, many of you will. But we don't address that in this course, okay? But my intuition tells me air resistance is not going to have much effect at these speeds, which are pretty modest, on something that dense and that big. If it's a ping pong ball, it's a little different. Okay, so net force at a point on the arc. Well, at any point on the arc, we can just pick one. At this point, everybody diagram just has mg down here. Okay, if you want a different point, okay, you got mg. And it may be negative mgj if you want to be very specific. Make sense? Okay. Yep. Yeah, just whatever you do, don't cough. That's the way you can be identified. Okay. Cough any way you need to cough. Your body's going to tell you. Okay. I doubt that we can identify participants by their coughs. All right, do we understand that? Okay, the point I want to make right now is just something for you to store away for a couple of days until we really start talking about energy. Because we are going to talk about energy a whole lot this week. Okay, as well as more about chapter 6, because you'll have no assignment in chapter 6. We're going to work in the whole idea of energy. Because that's what we're going to be looking at in lab. We're going to take data that allows us to determine energy. Okay? Work in energy. Okay, take the idea of work. If at either one of these points, we've got a gravitational force, which is the same at every point, right? Now, at the first point that I drew there, my velocity might look like this. Okay. So my displacement in some short time interval. Well, I guess I can pull this over a little bit and see the whole board. Okay. I can think of breaking this path up into small increments. Down here, small increments of path. Okay. So we have a small increment of path here. And we accept that idea that there's some small increment that's more or less parallel to B here. Which is our displacement. That's a delta S, the short vector. It's a displacement vector, okay? You can say that as this thing rises, it's going to be slowing down. Now, it doesn't slow down in the X direction, but it does slow down in the Y direction because obviously it's approaching velocity zero at this point. So if we multiply the beam by some small delta T, we can get a delta S. Don't worry too much about that. But okay, we're losing speed, which means we're losing energy of motion. Okay. If this thing runs into you, if it's a 30-pound cannonball, you want it to be going pretty slowly. Oh, if it runs into you, right? But if it runs into you here, it's probably going to do less damage than it would if it ran into you here, or heaven forbid here. Right? You can get a handle on that change in energy by doing the dot product of these two vectors. Okay. And the dot product of these two vectors is actually the work done by gravity on the cannonball or whatever it is. Okay. Thing you want to understand about this is that gravity isn't doing as much work on this increment as it would be, let's say, on an increment of equal length down here. Okay. Because your displacement here would be almost parallel to the force. So there's more force in the direction of displacement. Okay. Now you get more displacement for a given unit of time, but we're just looking at displacement intervals. You can assume that they're all about equal. So an equal displacement interval here as opposed to one here. First of all, your force is pretty close to parallel to your displacement in the same direction. So you're going to have a pretty positive result. Whereas up here, you're going to get a negative result because the component of force in this direction is much smaller than it would be there. Okay? Because force is almost perpendicular. It's approaching perpendicular to the path. Okay? And what we're going to call work is the product, the work over some displacement interval is just the dot product of the force with the displacement. Okay. Because of the angle, you get less work for equal displacement here than you would here. Not only that, but this work would be negative because these two have opposite, well, the component of this in the direction of this is negative. Okay. They're opposed. I don't want to get too technical on it right now. We'll do that in a couple of days. Once you get that idea. Okay. Meaning, of course, that the thing is gaining more energy per unit of displacement here, and it's losing here. That halfway makes sense? Think about dot products. Go back and review them because you're going to need them. All right. We'll develop these ideas in lab and a little bit in class next time, so I'll mention it again in maybe a different context. Okay. Enough of that. Now, I've got a coin. Resting at the end of this meter stick. That meter stick's too big for the camera. Okay, this meter stick. Back up a little bit. So I put a coin on it and I turn this thing, okay? Well, I'm not turning it that fast. If I turn it faster, you know that that coin's going to come off. Okay, I'm going to put the coin back here a few centimeters. And I'm going to tilt the thing so the coin falls off. Okay. If I rotate this thing pretty fast, what's the motion of the coin going to be relative to the meter stick? In other words, if you were right along the meter stick and didn't know you were rotating, well, you'd be able to figure out something's going on, either gravity or something is pulling that coin that way, right? You would be able to distinguish if this was like an intergalactic space and you couldn't see the orientation. You wouldn't know whether gravity's pulling it that way or whether there's some centrifugal force pulling it that way. Okay. Now, centrifugal force isn't a real force. It's an effective force. Depends on your reference frame. Okay. If we look at this thing from outside, we know that this penny or this coin is going to go straight when this thing rotates, unless something pulls it toward the center, right? Well, the thing is pulling it toward the center is centripetal force. And the thing that supplies this centripetal force is the frictional force. If we rotate it too fast, it's going to require more centripetal force than friction can supply, in which case you don't have the thing nailed down or otherwise restrained. It's going to start accelerating. Now, if you're riding on this thing, in what direction are you going to perceive this thing to accelerate? Radially, straight up. Okay? Now, there are other limitations on the acceleration. If I'm accelerating this thing too fast, it can slip off out of this. Underestimated how much work friction would do on this thing. Okay, so I go forward a little bit and I missed. Do it again. No way I'm going to. Now I lost my net. Oh man, another 50% hit to my net wealth. Okay. So I've got coins over here. Here's a quarter. I go into debt if I lose this. Okay, well, what happened there was this thing needed a force in that direction that friction couldn't handle, right? So there, if this thing's rotating, if the rotation is rate of rotation is increasing or decreasing, then we're putting demands on friction in this direction or this direction, right? If it's just rotating, then we're putting demands on friction, the ability of friction to exert a force in this direction. Okay. If it's not accelerating, it's just rotating fast enough and we set the coin down, the coin's going to slide along the meter stick. It's going to pick up speed. And it's going to go off the end, right? And when it goes off the end, it's going to have a velocity in this direction and a velocity in the radial direction. That makes sense? Think of being on a merry-go-round, okay? On roller skates. Well, we'll say more about this, but there are all kinds of questions that can be asked. Now I'm going to demonstrate something on the beam. So I'm not going to be able to record it, but we'll look at it again in lab. Okay, the thing we just talked a little bit about, referencing a beam on the axis of rotation, you put a box here, and you balance it with something over here. And you start this thing spinning, and within centrifugal force accelerates things. In the radial direction. So if you've got a car parked here, it's going to get accelerated that way, it's going to crash into this wall. Well, we call that a wall from our perspective, but from the perspective of somebody living in this box, this will be the floor. Because everything's attracting in the direction of the floor, right? And anything on the walls is just going to fall down. So we have this floor. Centrifugal force is an apparent force. It's not real. Feels real when you crash into the floor. Feels just like gravity. Feels just like a gravitational force, but it ain't. It's a lack of centripetal force. Okay. So what's really happening is the floor is accelerating toward whatever might be trying to float here. And the floor comes up and hits it. And you kind of want to get that idea. That's going to be important for analyzing our penny situation and so forth, because what happens to that penny now is that it's accelerated in this direction, as well as moving in the direction tangent to the rotation. Okay, so as far as that penny is concerned, there's this centrifugal force, it's pushing it out toward the end of the beam. That means that when it goes to the end of the beam, you get penny's path. And let's say the penny starts slipping at this point. accelerating toward the end of the beam. Okay. And that occurs maybe here. And here. Probably can't read that. That says free fall. Penny reaches the end and enters free fall here. Okay. The velocity of the penny at this point then is V tangential. Okay, because it is moving in this circular arc, but it's also moving radially. So its velocity when it leaves is not tangent. Okay. Now in my original model, polynomial I gave you, I neglected that one. Because I was thinking, well, that penny's or that magnet's only about this wide, it's not going to pick up much speed. Then I worked it out and said, well, picks up significant speed. So your actual velocity is going to look maybe more like this. So there's your initial velocity in the free fall. Okay. Now we can measure the coefficient of friction. I think it's between 0.3 and 0.4, somewhere around there. That's static friction. Kinetic friction is going to probably be a tenth lower. Ballpark. We can measure those things. We will in lab. We did it just heuristically, with a 60 centimeter meter stick. Had to raise the end up about 30 centimeters, had the magnet sitting on it. Then he started to slide around that point. Okay. That gave me an idea of what the coefficient of static friction would be. We got a tangent of that 30 divided by the 60. That was what it really was. I should understand that, having read the chapter and looked at problems and so forth. So I didn't want to talk too much about that. First of all, until I figured it out, which was 10 days ago, maybe. Whoops, we got that. Racking my brain for how in the world that penny went into that cup. And this still isn't an explanation, but it's one thing that I neglected to think about. Okay. Made what I thought was a reasonable assumption of tangential velocity. I think it's off the tangential by at least 10 or 20 degrees maybe. Now there are more subtleties to the acceleration of a penny that starts here and goes out to here. Because the further out it goes, the faster it goes. So it's picking up speed in that direction at a non-uniform rate. So you have non-uniform acceleration in the frame of reference of the beam. Because the further out, the greater the centrifugal force it needs to be. E squared over R. And the V gets bigger as you move out. And it's squared and the R is only first power. So all that goes together. Okay, well, I don't want to say too much more about it at this point, but we want to keep thinking about this. As I commented to my grandson on this would be a good junior level project for an undergraduate mechanical engineer. Okay. To actually design this, control the acceleration with some kind of a motor, put all the gears in shape, come up with sensors measure everything and maybe a high-speed camera, which would validate all the analysis. It's a very, very good project. We're not going to go that far with it, obviously. But it's a good thing to understand. I think it's a complex enough system. You can learn a lot by studying it. So we want to at least get the B squared over R stuff and understand this frame of reference stuff. Okay. You see other references to frame of reference in your text. This is just another frame of reference. Okay. Okay, another system we want to analyze. So far, this looks kind of like an outward movement, except I don't have a string from here to here. Okay, I need a string connecting these. It's going to be an outward type thing, except, I'm going to do something else. Put a block here. Sliding here, maybe with friction, maybe without friction. Well, let's consider frictionless first, but let's do this. Okay, so I've got a mass M1 here, a mass M2 here, and a mass M3 here. How are you going to analyze this? Okay, well, let's further specify that. Let's say this mass is greater than this. Okay, so we know we have more downward force in this end than we have on this end. Do we have any other vertical forces? Well, of course, we've got tension up here, right? Are the tensions equal? Well, I want to think about it a little bit. And you got the third mass. It does have a downward gravitational force, but the upward normal force balances it. Coefficient of friction is 0. Okay. It's worth drawing free body diagrams for all three of these and making sense of it to determine whether the tension here is the same as the tension. But I'll tell you, tension here has to be the same as the tension here, assuming frictionless pulling and by spring. And the tension here has to be the same as the tension here. But since this thing's going to have to accelerate, tension here can't be the same as the tension here. If it was, it would be in equilibrium. Now, if there's friction and enough friction to hold this thing still, if it's massive enough, have enough friction, then this tension is going to be equal and opposite to this tension, but nothing's going to accelerate. Okay. Instead of looking at those details, and you do need to look at those details if you want to answer the question, what's the tension here? What's the tension here? Okay. We can analyze the whole system. I say the net force is negative M2G plus M1G. Why do I say that? Why is this negative and this positive? Because we have rotation, and the positive direction of rotation is counterclockwise. It doesn't always have to be like that, but yeah, in this course for right now, it does. Because you're going to confuse yourself if you have to specify what direction of rotation is positive. It's always this way. And your right-hand rule with torques is only going to work if you know that that's the positive direction. That's a direction that your right hand would have to go in to rotate in this direction. That's going to be very important. Okay. So anyhow, here's net force. Okay. Now, the motion is in one dimension. I mean, things are moving in 2 dimensions in space, right? Okay. But the system can only move counterclockwise or clockwise. That's one-dimensional motion. You can describe the motion by one parameter. Okay, call it S. So if I decide that S is 0, with the initial, then S will be positive if it goes in this direction. S will become negative if it goes in this direction. Okay, you only need one number. If I tell you that this thing moves 10 centimeters this way, you know where it's going to be. If I tell you it's moving at 5 meters per second in this direction, you know what's happening with the positions. Okay, so this is very simple. Acceleration is F net over M. The M is now M1 plus M2 plus M3, right? Because all three masses are being accelerated. Okay. So if you memorize this formula, M1 minus M2 divided by M1 plus M2 times G, it's not going to do you a doggone bit of good on this system, is it? You want to understand why the acceleration is what it is by not bypassing the whole analysis of net force, which is pretty simple. And we did it last time. We did the M2G, M1G minus M2G over M1 plus M2 or whatever it was. That's a handy formula, but let that formula remind you of why. Okay. Feel free to use it as long as you are thinking about why it works every time you do it. Because then you'll be able to adapt it if this is here. And then if I put a non-zero frictional force, well, that's going to affect your net force, right? And then if M3 is moving in the positive direction, you're going to have a force in the negative direction, right? And that's going to say that you have minus U M3G. The acceleration is this, which is a little more complicated than a formula you can memorize. It doesn't have that M3 on there, right? So you see that there are plenty of variations in this, and you don't have to memorize a formula for every possible variation. It's not going to help you. Now, on a test, if you memorize that formula and get it for, no mass here and, no friction and everything, and work at that level, that's like low sea level. Okay, it's passable. Get you through the course, get you transferred into Virginia Tech, no problem. Okay, but if you want to make a good grade, and especially if you're going to go into an engineering field that has any rigor at all in physics, you want to do this. Okay. Okay.